All right. Now that we understand the discrete Fourier transform and we've seen the short time Fourier transform in spectrograms, I want to talk about an important caveat and pitfall that can happen when doing spectrograms. And so this relates to what we observed before. When we derived all this, we were very careful to make sure that we only included sines and cosines that went through a whole number of periods over the interval we were looking at. And we saw that if we violate that assumption, what ends up happening is the amplitudes of the sines and cosines that do go through a whole number period that we use to represent our signal kind of get smeared over a bunch of them. So I want to dig into this even more because, well, this is something that's very likely to happen when we window, right? We're kind of chopping little bits of our signal out and doing the discrete Fourier transform. Chances that we chop things at the end of the period are pretty slim. So we need to understand this phenomenon better. To understand this better, what we need to examine is the fact that when we say that things go through a whole number of periods and that we're representing signals that go through a whole number of periods, what we're really saying is we can imagine these signals as living on a circle. So if I take the interval that I'm looking at and I warp it, I'm saying this thing goes through a whole number of periods, so it should repeat itself once it gets to the end. Well, that's just like saying, imagine this living on the circle. And so what you see is a phase shift in that context corresponds to a rotation. So here I am shifting this thing. Notice when I shift it past this end, it shifts over here because I'm assuming this thing is periodic. I'm assuming that it actually has gone through a whole number of cycles on this interval. So it actually should meet up exactly where it started. That's the assumption that I have here. So it's kind of like another way to see it in the original domain, just on the interval here. Like, so here is an example that should look kind of familiar. Here's one period of a sawtooth wave. And as I shift it along, I can change the sines and the cosines, but I don't actually change the amplitude. But actually, if I zoom out, what I'm really seeing is, this looks a little weird when I just have one period and I shift it like this. What that's really doing is that's like taking a window in many periods and just sliding this thing through that window. So you can see it's actually a continuation of other periods. So it actually is. I know it looks like it's kind of jumping up here. It's got this, seems like it has this weird discontinuity, but really it's just continuing from another period, and then it goes to continue another period. So that's really what's going on. So this is all perfectly fine if we do this to a signal which does go through a whole number of periods. We can decompose that into sines and cosines that go through a whole number of periods, no problem. So in particular, if I just look at a pure cosine wave that goes through 3 cycles over an interval and I shift it along, I can see no problem. It's continuing itself just perfectly here. And I only need one sine and one cosine to represent it. The problem occurs when I use something that does not go through a whole number of periods. So here's really what the discrete Fourier transform is assuming. It's assuming that it looks like this, actually. So here's one that's supposed to go through 1.5 periods. But in order to get it to continue where it left off, it has to do this jump here. So this is actually the shape we're representing. We're really representing this signal here. I know we thought we were representing a cosine when we just looked at the window at the very beginning. But we're actually representing something else that needs many more frequencies to describe. And so yeah, I know it looked like this, but as we shift, we see it does this weird jump. And whenever you see a jump, you should think high frequency. We need sines and cosines that go through many, many cycles to make that happen over a short interval. So that's part of the intuition behind why we need so many. So do we just accept this? Do we just accept the fact that we're going to get a lot of this blurring in the frequency domain? Well, no, of course not. So we're going to figure out a way to massage the Fourier transform so that we can get rid of some of this. And so we're going to use something called a window function. Okay, so let's look first at a sine window function. So what we're going to do is if we have n samples, we're going to point multiply our chunks of audio by the following function. So we're going to multiply by sine of 2 pi n over n. Actually, just sine pi of n over n. Okay. So we're going to multiply our signal by a sine that goes through a half of a period. So let me just plot this real quick. What this looks like is this. So let's say n is 100. So I'll say, my window function is equal to np dot sine of np dot a range n times pi. Well, let me do it exactly with the equation. So np dot pi times. Okay, let me sample this at all the samples. np dot a range n over n. So let me plot this. All right, so it looks like that. So what this is going to do is it's going to damp down things towards the beginning and end of the period. So it would actually damp this down here so it wouldn't jump so much. That would actually be multiplied by 0. So let's see what this looks like on that same cosine that doesn't go through an integer number of periods. So if I just point multiply the window by this sine function, I end up getting the following. Oops, real quick. Okay, so this is the same thing, but notice how when I multiplied it by this function, it damped it down at the edges so it didn't jump like that. And so now, this was a frequency of 1.5 hertz. It's supposed to go through 1.5 cycles, and we see now very nicely that these two bins are activated. So that seems like it's working a lot better. Instead of bleeding into all these other frequencies, we actually see just the two bins that really should be activated. Okay. So that's nice. Just to show you another example, I could also take a square wave which doesn't go through an integer number of periods over the interval I'm looking at. And it looks like this. So this has a frequency of 4.5 hertz. So it's supposed to go through 4.5 cycles. But you notice the assumption behind the discrete Fourier transform to make this actually perfectly periodic, we end up getting this thing where we didn't actually have time to go down before we were supposed to start again. So when we windowed this, we ended up with, okay, so here is the beginning. That's what we actually look like. But you see, as I shift it and assume that it comes from something that's perfectly periodic, that goes through an integer number of cycles, I end up with this weird shape here. It's not actually a square wave, it kind of bulges out a little bit. So to fix this, I can do the same thing, where I multiply each window by the sine wave. And here's what I get instead. So this looks a lot better. I know it looks a little weird in the time domain, but in the frequency domain, this shakes out exactly the harmonics that are involved here. All the odd harmonics going down as 1 over the frequency. So this is, and we can see it's in between two, so it activates two of them right next to each other instead of activating all of these, instead of blurring out everywhere. So that's very nice. Okay, so let me show you how this works on the short time Fourier transform as well. So I want to apply windows to the short time Fourier transform. And I'm going to apply something called the Hann window, which is a little fancier than just half of a period of a sine. This one is going to be, actually, it really is just sine squared. So you could write that the window function of n is equal to sine squared of, or let me say it this way. Yeah, sine squared of pi n over n. But people more often write this as 0.5, using a trig identity, 0.5 times 1 minus cosine of 2 pi n. So let me just plot that and see what it looks like. And we're going to apply this to every single window in the short time Fourier transform. Okay, so I'll say, again, n equals 100. I'll say f is equal to 0.5 times 1 minus cosine of 2 pi. I get all my samples there. All right, let's plot this. So it looks like that. So it just kind of, it bows out at the end a little bit more, whereas the sine just went kind of straight down. So it actually changes its concavity near the end here. Okay, so this is a more commonly used one. So I'm going to do the same thing for the short time Fourier transform, but I want to look at the difference with and without this window. So what I can do is create that window function. I know I'm going to have to apply it to every single window. So what I'll do is, I guess I'll pass it along as a parameter here. And actually, let me make it a proper function. So I'll make it just like I did in the assignment, in the digital instruments assignment. I'm actually going to define a function and pass that function as a parameter. So this is called the Hann window. I'll just return a Hann window with n samples, and let me just copy and paste the code I did a moment ago. So that would have been this. So that's it. So I'll pass that along as a parameter window. Okay, then I'll just call this window function, and I'll just multiply every chunk that I take by this window function. Okay. So to see the difference, let me actually start with, I'll just return the constant first. But then I'll change it to be the Hann window. Okay, so let me start with this. So this is what we had before. And of course I have to pass, I have to rerun this. Run this, okay. So this is what we had originally. Let me change this so that it uses the Hann window instead. And it'll probably be a subtle difference, but okay. So what we see between these two is a little bit sharper. Well, we see a little bit less, I guess these stand out a little bit more from the background. Although it blurred them a bit too. But yeah, anyway, that's the Hann window. I guess it made things stand out a little more. But we understand the caveat that we have. We can run into trouble if we choose the wrong window length. Let me see. Okay, that's lower resolution, so that's not going to help me much. Okay, let me see. Let's compare that. So twice the window length there. Yeah, I would say that this is a little sharper in some ways. It makes it stand out against the background. And I guess that's the whole idea. I guess, yeah, you could see the bleed here a little bit more between harmonics. Here they really stand out from the background. That's what the difference is. Okay, so that's how you do windowing. Actually, now that I went through it, I realized I said I was going to teach you broadcasting, but I don't need to. So the Hann window is enough. So what I want to do is I'm going to have you do a little exercise where you implement something called the Blackman-Harris window. And then we can move on.